Good day everyone, I am Angelo Gaban and I will be introducing our video for cultural learning evidence in Calculus 2, whereas my partner Shawn Elbert Cabiles will explain the problem and its solution in the later part of the video. Today, our topic has been chosen is about work. Work is a scientific term used to describe the action of the force which move an object. When a constant force is applied to move an object, a distant amount of work is performed.
Hi, I'm Renz Gustilo, and I'm going to talk about work. Work in physics is defined as a product of the force and displacement. When an object moves a distance delta x along a straight line as a result of action of a constant force F, the work done by the force is W equals to F delta x. This equation is called the constant force formula for work.
I'm Abong in the application of integrals. In terms of physics, we see work, as per mentioned by Ivan, is the product of force and displacement, which is W is equals to Ft. However, most forces are not constant and will depend upon where exactly the force is acting. So, let's suppose that the force at any x is given by f of x, then the work done by the force in moving an object from x is equals to a to x is equals to b is given by this equation.
The SI unit of force is the Newton, and the SI unit of distance is a meter. The fundamental unit of work is 1 Newton meter or a joules. That is applying a force of 1 Newton for 1 meter performs 1 joules of work. In imperial unit that been used in United States, force is measured in pounds and distance is measured in feet. Hence, the work is measured in feet and pounds. Work is important for us so that we can determine the required answer to the solution in real life. For example, to determine the time or work to fill up the water tank, to find the total work when lifting heavy load, and also to find the work required when the spring stretches to the total of needed length, and to determine the force moving in a particular graph, for example, finding the force needed to move from x is equal to 3 and x is equal to 7. So that's all for the introduction of the topic we have chosen, and we finally concluded the explanation of its significance. Now, let's proceed to the next part of the video, a video related to work where my partner Shawn Albert Cabiles will discuss the problem and its solution. See you guys!
Good day, Miss. My name is Shawn Elbert F. Cabiles, and I will be showing or presenting you our problem related to work. And I will also explain its solution flowchart and how it is calculated. So without further ado, let the problem explanation commence. What you see here is our problem chosen for work, and I will read its words. A tank of water is 15 feet long and has a cross-section in the shape of an equilateral triangle with two sides feet long. Point of the triangle points directly down. The tank is filled with water to a depth of 9 inches. Determine the amount of work needed to pump all of the water to the top of the tank. Assume that the weight of the water is 62 pounds per feet cube. The most important key before calculating its final answer is to begin with the GRS scheme. G means given, R is for required, and S is for solution. For the given part, the given in the problems are the following. 15 feet long tank of water, sides of the equilateral triangle which is 2 feet long, the filling of the water of the tank is up to 9 inches, and the weight of the water which is 62 pounds per feet cube. For the required part, which is to determine the amount of work needed to pump all of the water to the top of the tank, and lastly, for the solution part, for the first part of the solution, we define x is equals to 0 to be the bottom point of the tank, and the height of the water in the tank to be x is equals to 9 over 12 is equals to 3/4 feet. Because all the other quantities are in feet, we converted this into feet as well. This means that we will be working in the interval 0 and 3/4 for this problem. Next, we'll divide the interval 0 and 3/4 into n subintervals, each of width delta x, and we'll let x sub I be any point in the ith subinterval, where n is equals to 1, 2, so on so forth, n. For each subinterval, we can approximate the water in the tank corresponding to that subinterval as a box with length 15 feet with the width of S sub I and the height of delta x. Shown to you is a picture of a water tank in an equilateral triangle shape which is about 15 feet in length. The red strip represents the box we are using to approximate the water in the tank in the ith subinterval, meaning to say that the red strip is useful for approximating the water tank in the ith subinterval. This is another picture of a water tank, but this time it has various measurements in its parts, where its width is 2 feet, square root of 3 when it comes to its height, and we have the unknown value of the red strip, which is S sub I, and we have another unknown value in the height from the red strip down to the flat surface, which is X sub I. And including here also is the width of the surface of the water to the bottom of the tank, which is 9 inches. The red strip again represents the box we are using to approximate the water in the ith subinterval. As stated in the problem statement, the cross-section is an equilateral triangle and with sides of length 2 feet. We included the height in the above sketch, and this is easy to get using some basic right triangle trigonometry. The picture below shows another sketch of the cross-section. Shown here is the values of every angle of the triangle and the values outside of the edge of the equilateral triangle, and we have the unknown value of h in the middle of a triangle. Because the triangle is an equilateral triangle, we know that each of the interior angles of the triangle must be pi over 3, and the length of each side is. The height of the triangle is the line that bisects the triangle as shown. Each half of the triangle is then an identical right triangle, and using of the trigonometry functions that we can quickly determine the height of the triangle. For that, we'll use cosine for this part. The equation process here, which is cosine pi over 6, implies to h the unknown value is equal to 2 cosine pi over 6, and we have the answer of square root of 3, which is also the value for the height of the triangle. Approaching with us right now is the second step of the solution process for the second step. We will need the volume of the box of water we using to approximate the volume of water in the ith subinterval, as represented by the red strip in the first two pictures from step 1. Our approximate volume is the volume of the box, and so we know that the volume for the ith subinterval will be as follows. Below is the equation, and it is being substituted. The equation is V sub I is equals to length times width times height is equals to 15 times S sub I times delta x, and that will give us the answer of 15 sub S sub I delta x. For the second step of the solution, we will basically find the volume to be in terms of X sub I. From the cross-section sketch with the red strip in step 1, we see that we have two smaller triangles. Well, actually, we have 3, but we need only 2 of them. The 2 that we need are the triangle with width 2 and height square root of 3, and the triangle whose width is S sub I. Example is the triangle whose top is the red strip and whose height is X sub I. Since these two triangles are similar, we know the following two ratios must be equal. Below is the equation for that. What we see here is S sub I over X sub I is equals to 2 over 3, implies S sub I is equal to 2 over square root of 3x sub I. Then we plug this into the formula of the volume, and this is what we got. V sub I is equals to 30 over square root of 3 times sub I delta x. Next slide shows you the third step of the solution. We need to know how much force will be required to overcome the force of gravity that is acting on the water in the ith subinterval. This will be approximately the force needed to overcome the force of gravity acting on the volume of water we found in step 2. Because we are working with the British system here, we can determine the value of force via the following equation. As F sub I is equals to weight times V sub I is approximately equal to 62 times 30 over square root of 3 x sub I delta x is equals to 1860 over square root of 3 x sub I and delta x. We are now in the fourth step of the solution, wherein we will find the amount of work required to raise the volume of water in the ith sub-interval to the top of the tank. For example, raise it a distance of square root of 3 minus x sub I. The equation for this is W sub I is approximately is equal to F sub I times square root of 3 minus x sub I is equal to 1680 over square root of 3 x sub I times square root of 3 minus x sub I times delta x. We are now at the final step of the solution. For this part, the total amount of work to raise all of the water to the top of the tank is approximately the sum of all the unknown value of W sub I for equals to 1, 2, so on, so forth, and n using this equation. Work is approximately equal to the sum of n and I is equals to 1 times 1860 over square root of 3x sub I times square root of 3 minus x sub I times delta x. The exact work mainly required is found by allowing n implies the infinity symbol, or basically, work is equals to lim, n approaches infinity, and the sum of n and I is equals to 1, and 1860 over square root of 3 x sub I times the square root of 3 minus x sub I times delta x. Shown here is the definite integral formula, wherein we have 3/4 as the upper limit and 0 is the lower limit. Then we have also the function here, which is 1860 over square root of 3x times square root of 3 minus x dx. Finally, we can determine the work required to pump the water to the top of the tank can now be determined via this solution. So the solution for the work is equals to the integral of 1860 over square root of 3x times 3 times square root of 3 minus x dx. Then we have this second process, which is 1860 over square root of 3, and we have the function here, square root of 3 over 2x squared minus 1 over 3x cubed. Then we have the upper and lower limits, which is 3 over 4 and 0, and that will give us the total answer of 372.112 foot-pounds. After lots of PowerPoint presentations worth of processing solutions, we finally got the final answer, and we conclude that the solution that the total work needed to pump the water tank to the top is 372.112 foot-pounds. Shown to you is the reference part with the link where our solution originated, so that we can avoid plagiarism, and as we all know that plagiarism is a very serious crime in college. So that ends our Calculus 2 Cultural Learning Evidence project, and thank you to our dearest Miss Ali Pomperada for all of the learnings you shared to the aspiring chemical engineers like us, the whole ENCH 1A class. We truly appreciate all of your thoughts and trained us despite the pandemic. God bless us all, and mabuhay CHE!